How y'all doing? We ready to go here? Yeah, if you did the homework, you're probably a little exhausted. And that's only half the homework for that section, right? It's a lot of work. And I think the second half is going to be even more work. Well, I know it's going to be more work. It's going to feel like more work. But this is a tough section. It's a lot. There's a lot in here. What's that?
Can we get an extension to like Wednesday of next week?
Let's see if you can do it by. Let's see. Oh, you have other tests? Do what you can. Do what you can. You know. Just we don't want to fall too far behind, right? Because when we come back next week, we're going to start the next section. So we're actually on schedule, which is good, but we're going to start partial fractions next week. And so you're going to need to kind of review partial fraction decomposition, which would have been a pre-calculus topic. And so you're going to maybe need to go back. I'm going to have some notes that you can go back and look at. But anyways, all right. Let's not get the carriage in front of the horse here. Let's wait till 9. We do have a new student joining us today. That's Joy. That's the chair of the math department. So every 2 years we have faculty evaluations. So if I'm nice to you today, that's why. All right. So I think, Joy, you're just going to be here for maybe half an hour or so. So what I'm going to do is I'm going to do the quiz at the end. All right. So that way we don't eat up time. So the quiz is going to be a homework problem, right? So, you know, hopefully you got through that. All right. Any questions before we start? I'm going to go over all the homework problems? Yeah. Yeah. Okay, so we are doing trigonometric substitution, right? And at the end of class, I did one of the problems, and I said, look, you know, this is where we're headed, right? But now we're going to formally kind of go through the procedure for this. We're still in 6.2. And last time I told you there's 2 sections to this. There's trig integrals and trigonometric substitution. So today is what we call trig sub. Okay, if you hear people talking, you go to the tutoring lab, hey, I need help with trig sub. They'll know what you're talking about, right? So trigonometric substitution, what we're doing is we're taking an integral and we're doing a weird substitution. That's what I kind of alluded to last time. This weird substitution that doesn't seem like it's going to make things better, but it actually does. So the question is, when do we do the substitution and what substitution do we make? And there are 3 different scenarios, 3 different cases, all right? So let me just try and kind of explain how it goes, all right? Say you got an integral and, you know, d whatever, I'll just say dx. What you do is you look at the integrand, right? And what you're looking for is one of 3 things. Okay, so in here somewhere, it doesn't matter where it is, what you're looking for is in here somewhere, either the square root of some constant squared minus the variable squared. Okay, so this is a constant being squared, and then this is subtraction, and then you have the variable being squared. So you're looking for that, or you're looking for that reversed, the variable squared minus a constant squared, or the last thing is the square root of the variable squared plus a constant squared. Now, because this is addition, this could be flipped around. It could be the constant squared plus the variable squared, but these two, the order matters. All right? So let me give you specific examples of these. Let's say you saw in there an example of this. Let's say you saw square root of 9 minus x squared. And again, this is just, it appears somewhere in here, okay? It could be mixed up with a bunch of other stuff as well, but you see that in there, right? In this particular case, what would a be? A would be 3, right? So this is a squared. This is a squared. So whatever number is here, that's a squared, so a will be the square root of this number. So for this particular case, a would be 3, okay? Let me give you another example of this. What if you had that? Would that qualify for this? Is this number a number squared? What number squared? The square root of 5. right? So here you would have to recognize that a is the square root of 5, right? Because if you square that, you get 5. So whatever constant is there, right, whatever constant's there, you just take the square root of it. And that's what a is, okay? Here, give you an example. Let's just flip these over. X squared minus 9, and then give another example, x squared minus 5. In this case, again, a is 3, and here a is square root of 5. Hey, while we're looking at this, when we have the square root of a squared minus x squared, can't I factor a negative out of this? Can't I factor a negative out of this and make that negative a squared plus x squared? Would that be legal? Can I pull a negative out of these two terms? Sure, right? And then if I reverse those, this would be the square root of negative, and then I could go x squared minus a squared. What I'm getting at is when you have a squared minus x squared under a root, you might think, oh, I can just take a negative out, and then I'm looking at this case. But you're not, because this negative right here is a problem. It can't come out of the root. You can't take a negative out of a root, right? That's when you start talking about imaginary numbers. So I just want to make sure you understand that there's no way that you can manipulate this algebraically and make it equivalent to this. All right, so this is a distinct case from this. This, on the other hand, you can change the order, it doesn't matter. You all good? All right, now this square root, let's go with this. What if I did x squared plus 3? What would a be? Square root of 3. Okay? All right, questions here? We look at the integral. We look in here. We're looking for one of these three cases. Now, if we see one of these three cases, each case has a different substitution that we're going to make. All right, so now I would like to talk to you about what substitution you make for each one of these. And lucky for you, it's on a formula sheet that I allow you to have on the test. So you don't even have to memorize this, although it'd be nice if you did. Let me see here. So this is the formula sheet. This is the one we talked about last time, trig integrals and trig substitutions. Right here at the bottom of the page, let me go one more zoom in here. Right here at the bottom, it tells you for each of the three cases what trigonometric substitution you're going to make. All right? So if you see the square root of a squared minus x squared, you are going to make the substitution what? X is equal to a sine theta. So if you see this, let me erase this stuff. That was just so you could make sure you recognize what it looks like, right? So here you make the substitution that x is going to be whatever a is and then sine theta. All right? Now, if you see this, what do? Careful. They're not in the same order. You see them? A secant theta. All right? And then the last one would be the a tan theta. All right? Now, I told you last time, that's not a very natural thing to want to do, right? To replace x with something more complicated. But it's the Pythagorean identities that are going to allow us to rewrite this ugly expression. This square root thing is going to turn into something nice with the Pythagorean identities. All right, so let's just start doing some examples. I think the best way to see this at play is to actually just do some problems. I'm kind of being ambitious here. I have 8 problems I'm going to try and do today. I don't know if we'll get through all 8. I'm going to really try for it. All right, see how it goes. So the first problem, I tried to pick some problems that show you a variety of, after you do the substitution, what type of integral you're left with. Because they're not going to all turn out to be the same type of like after you do the substitution, the path after that is going to be just, different for each problem. So I'm trying to give you a variety But just keep in mind that, when you get to your homework, you might get something that I didn't show you. It's only 8 problems, right? So here we go. First problem I'm going to do, I'll put these up on the board. There we go. So here are the 8 problems. Start there with number 1. You don't see that all right? All right, so we're going to try that. I also tried to pick some problems that you can't really do with any other method. There are some problems where you do see these expressions, where you can do them with like basic U sub or integration by parts or something we've already done. So these problems are ones that you pretty much get stuck and you're almost forced to do the trig sub. All right, so does everyone see the form we have here, one of these 3? Which one is it? Top, middle, bottom? What do we got?
Middle.
We got the middle one, right? And what is A for us over here? 3. So we are going to make the substitution. We're going to replace all x's with, yep, which will be, so x, here comes our trig sub. We're going to do x is 3 secant theta, right? So I'm going to just say here, let x be that. Okay, now, from here, the rest of this is just pretty much standard for every problem you do. After you make the substitution, you're going to differentiate that with respect to theta. So you're just going to take derivative on the left. Dx is, what's derivative of 3 secant theta? 3 secant theta tangent theta. So every time you do a trig sub, first thing you do is you differentiate it, all right? And then the next thing you do is you take the thing that you were looking at in here that made you do the trig sub, you're going to take that expression, you're going to write it down over here, and we're going to simplify it. So what does the square root of x squared minus 9 become? All right, well, replace your x with 3 secant theta. So what happens if you square 3 secant theta? What do you get? 9 secant squared theta, right? So if I square this, square both sides, you get 9 secant squared theta. Everyone follow that? What do I still have under there? Minus 9. Now, the whole purpose of this is that expression should simplify and become something very good, very nice. So we have to use now a Pythagorean identity. And to do that, we're going to factor 9 out first. Right? We can factor 9 from both of these terms. And then secant squared theta minus 1 from the Pythagorean identities from last class that we reviewed, tangent squared theta, right? So this now becomes square root of 9 tangent squared theta. And then finally, since I have now multiplication there, you can take square root of each one, right? And we should get 3 tan theta. There we go. Questions? So all of this is just the preliminary setup, okay? What I've done is I've said I'm going to rewrite all x's with 3 secant theta. I'm going to replace dx with 3 secant theta tangent theta. And wherever I see this, I'm going to replace it with 3 tan theta. And now I'm going to rewrite the entire integral in terms of theta now. So no more x's, all thetas. So we have now integral 1 over, all right, bottom left corner, x cubed. Yeah, it's that 3 secant theta, but cubed, right? So you have to cube this. That's, 3 cubed is 27. So we'll put that down here. 27 secant cubed, I almost did squared. Secant cubed theta. Okay, that's x cubed, right? What also is down here with that? 3 tangent theta, right? That's what the square root is. It's this. So on the bottom next to this is 3 tan theta. And this is where like a lot of students make a mistake. That's it. That's all they write. What am I missing? Yeah, I'm missing this, right? I'm missing dx. What's dx? Well, dx is 3 secant theta tan. Oh, my mistake. I'm missing a d theta here. Sorry. When I differentiated this, 3 secant theta, tangent theta, d theta, I even was going to make sure y'all didn't forget that. There, I forgot it, so it helps you remember, right? Don't forget it, right? Because you differentiated with respect to theta. So when we rewrite this integral, the dx here is going to be replaced with 3 secant theta, tangent theta, d theta. And now we have a new integral that looks terrible right now, right? This kind of looks terrible, you know, with all this stuff, but a bunch of stuff's going to cancel. All right? So let's just start wiping some stuff out. Gone, gone, right? Hey, gone, gone. And one of the secant factors can reduce out also, so this now becomes a squared. Are there any constants I can pull out? 1 over 27 can come out of this, so we can have 1 over 27 on the outside, integral. What's left in here? 1 over secant squared, theta. D theta, right? And then we can start thinking about last class at this point, right? The whole point I told you last class was we're going to do trig integrals so that when we get to trig sub, we know how to finish the problems out because you're going to have a trig integral now. And you look at that for a while, and then you realize that this can be rewritten. What's probably the best approach here? Rewrite this as what? What's 1 over secant? Cosine. So 1 over secant squared is cosine squared, right? So this is cosine squared theta, d theta, and we know how to do that from last class because that has an even power on cosine, right? And so when we have an even power on cosine, what do? Half angle identities, right? So this should take us, at this point, like in theory, if you did your homework and you feel comfortable with it, at this point you should feel like, okay, I'm finally to a point where I kind of know what to do from here. But we need to take it all away because some weird stuff happens in here, right? That we haven't really seen yet. All right, so we are going to continue, right? Continue here. We're going to say this is equal to 1 over 27 integral. Now I'm going to use the half angle, so I'm going to rewrite that as 1/2. 1/2 what? Cosine what? 2 theta. Good. D theta. And now I'm integrating that. Take the half out. Bring it out as a 1 over 54. Good. And then because these are two terms separated by addition, right? I can just do them term by term. So the antiderivative of 1, careful. Theta, right? We always keep track of our variable here, right? So the antiderivative of 1 would be theta. And then this we've done a lot, right? We just have to make sure we keep track of that constant. So, good, I think y'all are there. So I'm actually taking the antiderivative now, right? So no more integral sign. Okay, 1, that's theta, plus, what did you say this is? 1/2 sine 2 theta. There's no negative there, right? Because antiderivative cosine is sine. And then we have plus c. Okay, we're not done, right? We're not done. Because the original problem was in terms of the variable x, we're in terms of theta. I always think of this way. It's like if I ask you what's your favorite color, right? And you tell me 7. 7's not a color, right? Like, so we have an answer, but it's not in terms of what I was asking, right? We were asking about x. What's the antiderivative with respect to x? And you're talking about theta right now. So we need to get it back to x. And this is where we're going to utilize what?
The reference triangle.
The reference triangle. Good. Right? So I'm going to draw a triangle, and I've erased it. Oh, well. Okay. So somewhere, what do you go to the triangle for? Where do you go to go make the triangle? What do you look at? The original trig sub, right? The original trig sub that you made was x equals 3, what was it, secant theta? That was the original, I erased it. Okay, that was the original trig sub we made. We're going to use this equation to construct a right triangle. That's going to be our reference triangle, and then from that we can figure out any trig function value off that triangle. I only need, well, what do I need? Wait a minute, hold on. We'll deal with that in a second. Let's just get the triangle made. So I'm going to take that equation, I'm going to divide both sides by 3, right? And then from this, draw a right triangle, label this theta. Secant is which side over which side? Hypotenuse over adjacent. So this should be x and this should be 3. And then once we have two sides of a right triangle, we can solve for the third side. Now I'm not going to go through that, but I will do it. It's x squared minus 9. And I told you last time that on your triangle, like 99% of the time, you're going to see the thing that was in your integral somewhere on one side of your triangle. Sometimes there's some issues with constants that can scale it and it can become a little bit different, but most of the time, this is going to be on one side of your triangle, all right? All right, so from this, I can say what sine is, cosine, tangent, cotangent, right? Anything about theta, about anything about what? Any trig function of theta I can tell you about, right? But what's in our answer? Not sine of theta, sine of 2 theta, and that is a problem. Because when you look at sine of 2 theta, let me do it over here. Sine of 2 theta, right, is not 2 sine of theta, right? You can't pull a 2 out of this, right? But what you can do is you can go back to pre-cal and you can remember the double angle identity for sine that turns sine 2 theta into 2 sine theta cosine theta. This is a big identity in pre-cal. Hopefully your pre-cal instructor told you that. Okay, this is a big one. All right. Does that look familiar to you? It's on your formula sheets, but you need to know about it, right? And now what this allows me to do, it allows me to take sine of 2 theta and turn it into something that's in terms of sine of theta and cosine theta, and then I can use my reference triangle because my reference triangle has everything to do with theta, right? So I'm going to come back here. I've got to replace this sine 2 theta with this, right? I'm going to go up here. 1 over 54. All right, we have theta plus, now when I replace that, what's it going to become? Let me do it right here. 2 sine theta cosine theta. Doesn't that half and that 2 go away, right? So I can just put here sine theta cosine theta, right? Sine theta cosine theta, all right, plus c. All right, so let's just take a look at what we have. Am I going to be able to use my triangle to get sine theta? Yes? Cosine theta? Yes? What about theta, though? Do we know what theta is in terms of x? Yeah, look at this is my connection between x and theta, right? So I need to figure out if I can solve this for theta. There's a couple of ways you can do it. A couple of ways. One way to do it is just divide both sides by 3. And then arc secant on both sides of the equation. So I just take the inverse secant on the left, and then inverse secant on the right. When I take the inverse secant of secant, that just gives me the theta, right? And then I know what theta is, right, in terms of x. That's one way. Another way you could do it is you could rewrite this as 3 over x is cosine theta. Okay, so I'm just basically saying the reciprocal of secant is cosine, right? And the reciprocal of that is this. And so then I could do the same thing, take the inverse cosine on both sides, and get cosine inverse of 3 over x is theta. There's actually a lot of different ways I could have done this, but these two ways are probably the most common that you would see. I think in the book you probably see this done. Is that all right with everyone? All right, I'm going to do this way, all right, for a reason. I'm going to show you why in a minute, but I'm going to do this one, all right? So I think I'm pretty close to having an answer here. 1 over 54. Okay, theta, which I am saying is this, cosine inverse of 3 over x. And then I have plus, and then sine theta. Sine off of this, sine is opposite hypotenuse. So the square root of x squared minus 9 over x times cosine theta, right? Cosine theta, which is the adjacent over the hypotenuse, so 3 over x, and then plus c. And that is our answer in terms of x. Now we can do a little bit of algebra on this to clean this up, but we've gotten to a solution, all right, in terms of x. And it only took us 24 minutes, right? I'm debating right now, do we want to check our answer? Do y'all want to take the derivative of that and see if we get back the original? Y'all don't want to? No? I think it would be a good exercise. We just don't have time, right? But okay, I won't do it on this one. Maybe on another one. All right, any questions? There's a lot going on there? Yeah? Yes?
So you said you wanted to use the second one because...
Because I was going to check my answer.
Oh, okay. But
And so if I needed to take the derivative, then I would have gone to, you are all familiar with the derivative of inverse cosine from earlier this semester. So it would have been easier for me to reference that than to reference this. Even though we would have a formula for this, you'd be more familiar with this one. Thank you for asking. That's why I did it. Okay. Any other questions? Yes?
What did you get the square root of x squared minus 9 over x? Where's that from?
Okay, so that's sine theta, right? And that was off the triangle, the reference triangle, right? And sine is opposite. Sorry, I drew this wrong. That was not our triangle. This was our, that's not our triangle either. This is our triangle, right? That was it right there. So sine is opposite over hypotenuse, right? And then this one is cosine, which is adjacent over hypotenuse. Any others? Any other questions? Yes.
Professor, this is just a real homework quick, because I know we have a schedule. One of the questions you got it in terms of cosine, and I got it in terms of sine. Technically the same answer. If you change the identities around on the test, are you going to implicitly tell us to get it in terms of cosine?
Nope. Yeah. No. So the question was, you know, sometimes when you work a problem, you might go a slightly different path where you use cosine, I use sine. Our answers might look different, but I'll be able to follow your work and know if it's, as long as it's all right, it's okay if our answers look different. Remember when I typed in the answer into Wolfram Alpha the other day and it didn't look anything like our answer? Same principle. It's like there's a couple of different ways you could do this. Couple of different ways it could look, I should say. All right, let's get to the second one, yeah? I don't know if we can get through 8 at this pace, right? All right, let's see. I'm going to have to pick and choose here which one I want. Let's do this one. No. Trying to see which one. Okay, let's do this one. Let's do number 4. I'll scroll down to it in a second. The fourth one, we're using a different variable. We're going to use t to the 5th over the square root of t squared plus 2 dt. So our variable in the problem is t, right? As opposed to x, no big deal, right? All right, which of the forms do you see? What's our trigonometric substitution? A tan theta is going to be our trig sub, right? A tan theta. We're looking at the second one there, except we have it reversed here, which is okay with the plus, right? With the plus, it doesn't matter which order these are in. So A for us is what? Square root of 2. Square root of 2. So I'm going to make the substitution, what? Oh, careful. T equals, right? T equals the square root of 2 tan theta. We're going from t to a new variable. Derivative now, right? Take derivative. So derivative dt equals root 2 derivative tangent secant squared theta d theta.
That's just constant, the root 2.
Root 2 is our constant. That's right. It just comes for the ride. Exactly. Yeah, when you take this derivative, right, this a is just going to keep coming with us as a constant. Now I've got to figure out what the square root of t squared plus 2, what does it become? Let's see. Well, t squared, what happens if you square this? What do you get? Square the root 2, 2. Square the tangent, tangent squared. So you get 2 tan squared theta plus 2. Y'all seeing where that's coming from? Yes?
Why are we setting it equal to a root again?
Because in the form, right, to use this form, we have to have something that looks like a number squared plus x squared, right? And this number squared, right, that number squared for us is 2. So a squared is 2 for us, which means if you take square root on both sides, we take the principal root, the positive root, right, you get root 2.
I was just, yeah, just that, why we were setting that equal under the radicand is what I was understanding.
So are we good now or no?
I think
This right here, t squared, is this squared,
so. Yes.
right? So you square that, you get the 2, you square that, you get this. And then you still have plus 2 here,
Right,
you know?
yes.
You sure? Okay. What now? Factor 2 out. They both have a 2, right? This is going to happen every time you do this. This is going to happen if you do it right. You're going to factor something out. And what's left in here, in that parentheses, should be a Pythagorean identity. What is tangent squared theta plus 1? Secant squared theta. So this becomes square root of